Hello, everyone. I'm just going to double check that I'm actually on YouTube right now. I think I am. I think I'm live on YouTube. It says I'm live. Okay, that's good news. Yeah. So this is Bex 3.0, or it's a 0.3. T-Nids and F-Nids. So I'm going to talk about what those are in a minute. You might think they're true and false, but they have nothing to do with true and false. Because as everyone knows, the letter for true is I, and the letter for false is O. Let me go ahead and just let me reintroduce Bex real quick, because I have been streaming about this. I streamed about this for about a month on Twitch and recorded a bunch of it and did not upload it to this channel, which I meant to do. So let me just real quick talk about what Bex is. First of all, you have this lovely red IDE. That is my color code for Bex. Get used to it. My number one question is, why is it so red? Well, I just picked red. Actually, the color scheme is, the color red is supposed to be good for your eyes. I read that one day, and the next time I picked a project in my IDE, I set the color to red, and so now whenever I open this particular workspace, I get a red workspace. So okay, so github.com tangent storm, that's me. Actually, my name is Michael. I don't know if you don't know that. Bex is a binary expression toolkit. It is a Rust package for working with Boolean expressions. I did cover it a little bit in a video called J and Bex versus Primordial 15 on my other video, on my other channel, my quote-unquote main channel, non-streaming channel. And last month when I was streaming on Twitch, and I spent a lot of time, basically, I made the thing 100 times faster, so it's like, nice and speedy, almost on par with the people who made the benchmark that told me I was slow. So not quite there, but pretty close. So the idea is you have, let me show the pitch I've been making before on. So I have observable HQ is a tool for making notebooks, and just real quick, the idea is that you have abstract syntax trees. So an abstract syntax tree is a concept from programming where you parse a sentence, or you parse your input, and you get a tree structure. So here, for example, we have a string that, let me make that a little bigger. Yeah, okay, I should be signed in, right? I guess I don't need to be. So observable is cool. Go to observable HQ to, that's my pitch. Not sponsored by them or anything. So anyway, A and B. So I have, the string, capital A space, lowercase a and d space. These are the bytes of the input, and then it gets parsed into a tree that looks like this. So, you have a node here that represents this variable A. You have this symbol here which represents the AND operation. And you have B and C, and then they are being fed into this XOR operation, which is also spelled not equal when you're talking about bits. And then the result of that gets fed into here, into the other side of the AND. So that's the abstract syntax tree part. So we parse. There actually is no parser. You just construct the abstract syntax tree directly. But in theory, there would be a parser. Could be a parser. There is not one yet. Actually, there is a very primitive one that is like RPN based. So you would type you would type it like this. And first of all, you don't use the letters A, B, and C. You refer to variables by their number. So it's x0, x2, x1, XOR. So this is saying take these two things, XOR them together, and then take the result of that and XOR it or AND it with x0, and then show it. And when you type that into the console, you actually get this diagram, this particular diagram with that color scheme and that layout. Everything looks exactly like that, and that pops up on your screen. And then you can copy and paste it into a, or actually, if you say the word dot here, you can get text that you can copy and paste into here, and then it, it looks like this. It says digraph, and it, says how to make that drawing. I don't want to help that. Okay, so now we have a graph, both a visual graph and that says won't help. I do not want to help. we have both a graph inside the computer, and we can draw that graph. And then the idea is now, this only has 3 input variables, but we could be dealing with hundreds of input variables, thousands of input variables, millions of input variables. That could represent like a whole CPU or something like that. And you want to say, well, like, what is if you set the inputs to this, and the memory, some of that memory bits could be used as inputs to the state, right? And then you say, well, what is the output when you have all these input bits, right? And that's kind of the goal we're looking for. Like one of my examples, the primorial 15 example that's in this other video here. The idea is you're multiplying a bunch of prime numbers together. In fact, the first 15 prime numbers together, we get the number. And then, so now the question is, okay, make the circuit for a multiplication, a generic multiplication. And then I'm going to say the result is this big prime number, or not primorial number, this big composite number. And the question is, like, what were the 2 inputs? So if it's that primorial 15 happens to be the biggest primorial that fits in a 64-bit integer. So the question is then, let's say there were 2 32-bit integers. We'll call them x and y. And we're going to say x is the smaller one, so x is less than y. And then tell me what could x and y be that would multiply together and give you that thing. So it's a way of like partitioning all the primes into 2 32-bit registers, 2 32-bit products, and then saying, what are all the possible products that could give me this giant prime number, this giant primorial? And there are actually like several thousand answers. And they're encoded in a test case in Bex, and Bex cannot solve that problem yet. So Bex cannot do it. It doesn't know anything about math. It only knows about bits, and the goal is to. I wouldn't say that's the goal. That's like a benchmark, and the benchmark would be met if the case would be solved if I could get Bex to that point, and then I would have to find a harder test case, probably primorial 16, right? And right now, and also because there are lower primorials, and then I have a ladder of benchmarks, and so some of the lower primorials I'm able to solve like instantly, and then dividing them into like 4-bit inputs to make a 16-bit input or something like that, or make an 8-bit input or something like that. And then when it gets up to whatever the first or second 8-bit one, it just doesn't do well with some of the solvers. There's like multiple approaches to solving things. Anyway, I'm getting ahead of myself. So to actually solve these things, what we're going to do is we're going to say, okay, what does it mean to solve it? Solve it would mean tell me a set of assignments for x0, x1, x2 that give you that make the entire operation true. So obviously, if x0 is false here and you're ANDing it with something, then false and whatever it is false, and so that can't make it true. So x0 has to be true, right? And then these have to be different, and then that's the answer. But that's me knowing about logic and doing things, and Bex applies a more, well, that's one way of getting at it, right? Bex could apply that heuristic. It maybe applies that heuristic, but it in practice, could apply that heuristic. In practice, it does not. And it doesn't apply the heuristic I'm about to show you, but this is an algorithm that you can apply to any Boolean function to solve it, right? So basically, you make 2 copies. So you copy this whole thing, copy and paste it twice, copy it, paste it, and then you set one of the variables, say x0, to true and to false. So this is false, this is true. E is for, it's actually, it's called top, and this is bottom. And this indicates false, this indicates true in, I guess it's from abstract algebra, I don't know. I don't know what these symbols come from, but they're now used in Boolean logic all the time. Boolean, and named after George Boole. Right, so then we do the same thing again. And recursive, we do this iteratively. So now we put an x0 at the top, and we're branching. So this dotted line, so notice the arrows are going up. So that's data flowing up towards a solution. But here we're saying start at the top and branch. So we've got some data flowing up. This is the AST part. You've got multiple expressions. And then this is what's called a decision diagram part. So up here, we're saying start with this variable, and split between these two things. So if it's a dotted line, we're going to take this path. So I'm sorry, if x0 is 0, the input bit is 0. The 0th input bit is false. Then we're going to take this path and evaluate here. So where we've substituted in 0, false. And here where if it's 1, we're going to substitute in true. And so you're basically using this bit to choose between one of these two expressions that have been slightly modified. All right, so now we're going to do the same thing with x1, x2. So we repeat with x1, and now you get basically 4 copies of the original, but all with the x0 and the x1 filled in. And then same thing with x2. Oh, I didn't do that. I didn't actually draw that, but you would do the same thing. You would have 8 copies. So it gets bigger and bigger each time, but it also gives you chances to simplify, because as we said, anytime it's true and something, we could remove this whole branch and just go directly to the XOR. You just remove the and true part. And here we have the and false, so we could just go directly to false. So this could go directly to false, and we can simplify along the way, basically. So this process of branching and simplifying will, if you keep doing it, will eventually lead you to what's called a binary decision diagram, where you start at the top and you follow the branches, the path all the way down. So if x2 is if x2 is 0 and x1 is 0 and x0 is 0, then you get false. And likewise, if it's true and true and true, then you get false also. All right, so this is an uncompressed binary decision diagram. It's fully expanded binary decision diagram, but there's a lot of redundancy here. So whenever you see you're branching on a variable, and no matter what branch you take, you get to the same place. Well, you might as well just remove that branch and optimize by just putting the false here. And then likewise, whenever you have a false, whenever you're branching on a variable and you're going to false or true, if the variable is false, then the answer is false, and if the variable is true, then the answer is true. Then you can just ignore these things and just link directly to that variable. And then also, like you see here, this is x0, right? If x0 is false, then it's false. And this is the inverse of that. This is not x0, right? With the not operator applied. And so we flipped it. And so you can reuse the same node. And so the idea is that for this branch, you would just have a branch going right here, but encode something in the branch, add a little bit to the branch itself that said, for this link, just invert the tree under, the diagram underneath me. All right, and so you keep doing that, and you get this thing called the reduced ordered binary decision diagram, an ROBDD, which is like the main kind of BDD everyone uses. So when people say BDD, or when I say BDD, I'm now referring to this. This is the thing I'm talking about, and it looks like this. So this information and this information are exactly the same. This is just uncompressed, and this is reduced. Yeah. So basically, if the high and low, the two reduction rules are: if the high and low branches of a node point to the same destination, then you remove the node and just link directly to the destination. And then if any two nodes anywhere in the tree have the same the same branch variable, and I call this the low branch. The dotted line is the low branch, and this is the high branch. So if they have the same high and low pair, and the same branch variable, then you just replace the entire. You only make one copy of it, so you just make a link to that existing node, basically. And so those are the two reduction rules, and the ordered rule is the fact that we kind of implicitly got ordering from the way I constructed it, but ordering just means that if you start at the top and you go down, you always decrease in value. Or in the literature, they increase, but they shouldn't do that. They should decrease for reasons that make sense to me and have to do with caching, right? You always have a 0th variable. You may not necessarily have a 900th variable, so it makes sense to have 0 at the bottom so you can get more cache hits, I think. One of these days I'll probably write a paper and tell them all they've been doing it wrong. Anyway, that's a BDD. That's what BDDs are. That's what Bex does. It's not the only thing Bex does, but it's like one of the things Bex does, and it's used throughout Bex to to create a compressed truth table. So basically, this line right here, this line of boxes, or this row of bits, is a truth table, and this is a way of compressing it. But that's a little bit misleading because here false and true are nodes, right? So they're nodes in the graph, and in practice, whenever you refer to a node, that could have been a pointer to a structure in memory. But in practice, rather than using a pointer, I use this thing called a NID, a node identifier. And I said, well, you know what? It's a 64-bit thing, just like a pointer, but rather than actually store, this node as like in the database, have a entry in the database that said false and an entry in the database that said true, I was like, well, you know what? What if I just use some of those 64 bits to like encode the fact that this is a constant, right? So, okay, so I've got a NID that is always false, and that's called O, capital O, and a NID that's always true, and that's called I. But actually, O and I are just the same. Actually, there's just O, and then O with there's a, the NID also contains that invert bit I was mentioning. So if oh, that's actually wrong. That's missing a. There should be a little circle on one of these. There should be a little circle here. I'm going to write a note to myself that I need to make that little circle. So on, whoops, some notes from Bex from my previous benchmarking, but like on here, bottom BDD is missing. You can't see that, but I'm just writing a note to myself. The bottom BDD is missing the invert, the little circle. An invert. Okay. Yeah, because because these two are inverted. Yeah. Anyway, so in practice, only these three nodes are actually stored in the database. So if I actually did this, my database would have a node representing. In fact, I believe yeah. So this pops up as being x0, and this one, I know you can't read that, but that says that's. Well, it says VX1, but it should be V1. And it means just and V1 : 0. So it's the first. Oh, that's kind of a weird way of writing. Yeah, I might need to clean this up a little bit. But the intent is that this is a node that branches on X1. This is a node that branches on X1. And they're different, so they have different in and out branches. So these are two separate nodes that are stored in the database, and then the third node, chooses between them. And the way you read this is, you say, look at X2. If it's low, if it's 0, you go to this node. If it's high, you go to this node, and then you just follow it down all the way to the end. And then to reconstruct the whole truth table, you just enumerate every possibility. You start out where they're all 0, and then you say, well, 0, 0, 1, and then you say 0, 1, 0, and then you say 0, 1, 1, and you just count in binary. And then you follow every possible path. You could also have the case where like something is missing, and then you just imagine that it's there, and then so if this went directly to X0 from X2, then you would say, well, no matter what X1 is, you follow the link to the same place, but you still have to count when you're counting in binary. When you're enumerating, because the truth table will always be, for 3 inputs, will always be, one input would give you 2 possible values. You say, well, is it what happens when it's false? What happens when it's true? You double that when you add in the second bit, so now you have 4. So it's x, 2 to the third power for 3 bits. So if you have 15 bits of input or 16 bits of input, then you have 65,536 entries in your truth table, because that's what 2 to the 16th is. Anyway, I'm rambling here. This is how Bex, this is one way that Bex stores the answer to your question. One of the benefits of this is that it's called a canonical form. So if the statement is never true, then it will evaluate to just the single node false or zero or O, capital O. And if it's always true, if it's a theorem, then it will evaluate to the single node I, which is the true value. The idea is that O looks like a 0 and I looks like a 1. So you can't name constants with a. I could have called them K0 and K1, but I just chose to call them O and I because it looks nicer. It's a visual pun. Okay. And so if you wanted to do a SAT solver, for example, out of this, then you would just construct the BDD for your input, and then you would look at it and say, well, is it false? Is it O, capital O? Well, if it is, then it's not satisfiable, because that means there's no satisfying answers. And if it's anything else, then it's satisfiable. And that's the answer to your SAT score. Okay, so that's that. There are interesting properties of this, like, you know, once you have it in this form, they can be easily combined and so forth. And as I said, I was dealing with in version 0.2 last month. I've been working on this for several years, but the version numbers are very low. Right? It's not stable. And if I go back to this one here, I don't think maybe I don't have a link to this. All right, so if you go to, what's they're called? It's the Cybola? Give me a second. What is it called? Well, it's Biodivine. Oh, come on. Biodivine BDD. All right, well, they did a comparison to me. So here's me, Bex. I'm like the worst in all cases. HUD is kind of the industry standard. LibBDD is their thing, so they got pretty good results across the board for different kinds of circuits, and I was terrible. But this is old, so in over the past month, I've come very, very close to these numbers. Not quite, yeah. So much better, but not close enough. And part of the reason is the way that I do composition of these things. I wanted to link to the. Oh yeah, Cybola is what I was looking for. Cybola is the Systems Biology Lab. Systems Biology Laboratory, yeah. In a city in Europe with an interesting name that has no vowels in it. Brunn or something? Yeah. Oh, and Brno, that's what it is. Brno. It does have a vowel, just not where you'd expect it. Okay. Anyway, so I guess that's in the Czech Republic. We'll call it Czech Republic. Does not matter. I mean, it matters to them. In the Czech Republic. Okay. Anyway, not relevant to what I'm talking about though. So anyway, they made this thing, and so I'm kind of competing with them, and I got pretty close on the benchmarks. They have not updated this picture because why should they? And when I blow them out of the water, I will tell them to come update their pictures. But to not besmirch Bex, the good name of Bex. But I'm still not there yet. I'm still about 10 times on my benchmarks. I'm quite a bit. I'm about 10 times slower than them. But it's you know, the benchmarks run on like, you know, nanosecond scale. Anyway, so all of that is to say that there's improvements to be made, and this is a process of ongoing improvement for me. And so today I checked in this. I've been on vacation for about a week, and over the vacation I was thinking about this. This is something I've been thinking about for a long time, and I decided I would do some work on it. And so the idea has to do with, in fact, I did this. I had started it right before I left. And so a week ago, I started working on some actual code, and I checked some code into the Bex repo here. And I have this idea now for like to refine it. So I have not done any testing on this code. I just wrote it, which is not something I normally do. I normally test up front, but I just kind of wanted to get it out in a hurry. And so there's some completely untested and I believe probably wrong code right now for doing these things called F-Nids. So I go to docsrs.bex. Yeah. So as I said, we have this thing called nid, and yeah. So a nid represents a node in the base, and it's a base being like a database of these nodes, and it's a node identifier. There's two constants right now called I and O. But what I would like to see, you know, I'd like to extend this idea. So I think what I was trying to say earlier is that I store the constants. I don't store the constants in there. I don't store the variables in there. I only store the actual branches. So if you just have a variable, it's never stored. It's just that can be represented by the nid itself. So there's a bit in the nid that says I'm a variable. Okay, yeah. So I guess you can't see that from the but you can see there is. But you can ask the vid the node, are you a variable? And there's actually two kinds of variables. There's an actual input variable, and then there's this thing called a virtual variable. That basically the idea is that, you know, the way Bex works is that you take this thing. You know, it doesn't actually follow the algorithm I talked about. It'll basically take this node and say, well, this is virtual variable 1 or 0, and this is virtual variable 1, and it kind of looks at them and says, well, okay, now let me take virtual variable 1 and define it in terms of its input. So now we get rid of virtual variable 1 and we get x0 and virtual variable, we get rid of virtual variable 0. No, I'm sorry, you start with the highest one. So we get rid of virtual variable 1 and then we decrease it. We decrease the virtual variable counter, I guess, by removing it. So we delete every reference to virtual variable 1, which was at the top, and now we redefine it in terms of virtual variable 0 and x0. Well, then you have to get rid of virtual variable 0, and so you have to define that in terms of these two. And at every step, we build the BDD or some other format, some other canonical form. And so that's kind of the algorithm that Bex uses. All right, so that's what a virtual, that was kind of just a side note, a tangent. So anyway, yeah, so now the question is, what do we do? Or, you know, I want to extend this idea of not having a node, right? So I don't actually need to store any of this. Like, why do I need to store this graph structure when this bitmap, you know, all of these graph structures represent the same function. They're just different ways of drawing them. But this line right here, just this row of bits is 8 bits, right? Is the truth table. Well, I've got a 64-bit node identifier, and I need to use some of those bits for like header information. But the idea is that I could have a bit that says, hey, has a truth table in it. And then I've got 32 bits over on the other side of this thing, the side that isn't the header. And I can say, well, here's 32 bits, just store a complete truth table in there. And so that gives me 5 layers: x0, x1, x2, x3, and x4. Right? So 5 entire layers of this decision diagram can just be chopped off. Of every diagram can just be chopped off and deleted and kept with a truth table. Right? So that concept is what I'm calling a T-Nid. So it's a table nid, right? Right now, the only table nids are the ones that are called isconst. And there's actually a bit called that I've named T in the source code. So if I go to nid in the source code and I just look for T, const T, I was thinking of it as like a magical variable on which that branch, because I was only thinking about BDDs. But basically, there's a bit that is, I guess it's the third bit. So the highest bit is the invert bit. And the next bit, it says, yes, it's a variable or not. And then the third bit says, is it a T or is it a table or not? And so you could be some combination of it. The lowest 4 variables can have a truth table in them, and or lowest 5 variables, x0 through x5 could have truth tables. Anyway, I want to extend that idea to have any function of 5 variables should be stored directly in the nid. Any function of 5 or less variables, or 5 or fewer variables, should be stored directly in the nid. And that's what I'm shooting for. That's this idea of a T-Nid, a table nid. Then you say, well, okay, now I can represent a function with a truth table. So if I want to represent a function of 5 input variables, let me give you a distinction, like a concrete example. So there is the truth table that you get when you take those 5 input variables, ignore 3 of them, and you just say, like, if you call them A, B, C, D, E, which I actually have this. I usually do this in J, right? So, so let me just pull up J real quick. I'll give you a concrete example. This should be part of the standard demo for. Okay, so tools, session font, and we'll make this. I'll console this. I think I upgraded J, and so I don't have my fonts or whatever. Hopefully that's readable. All right, so we can say I'll just make the thing first. So you count in binary, like you want to enumerate every possibility. So 2 to the 5, right? That's 32. Going to count up to 0 to 31, and then show me that in binary. Okay, but that's the wrong orientation, so let's transpose it. And then we're going to say A, B. Actually, we want this one to be A. This is the smallest one. This is our x0 is always this pattern. So reverse it, and then we're going to assign them. And actually load UMAT, just so you get to see the pretty picture. You can say this, but UMAT this, and you get this nice little picture here. So that's the signal space, right? So that's the x0, x1, x2, x3, and x4. And of course, it keeps going, but this is 32 bits long, so any combination of these can fit in a 32-bit table. Anything else would be a 64-bit table, which I don't have room for this representation. I kind of think that anything up to about 20 bits, which would 20 bits, I think I calculated, winds up being about 8K of memory. And so why not just have that chunk of memory floating around rather than doing all this node stuff? Like when you're combining things, why not just like put them together into a truth table and just use truth tables So then you've got contiguous memory. You're just doing bit operations, and it should just be very, very fast to do that. But whatever. Okay. Right. So the idea was I was now going to say A, B, C, D, E is equal to these things, and so we get A, we get B. Okay. And now when I say what was the example I wanted to do? Going all the way back, I wanted to say A. What do I want to say? I wanted to give the example of A and B. Oh, right. So I want to make the distinction between T-nodes and F-nodes. So a T-node would contain this truth table. It's 32 bits long, right? And if I say B and C, right, I get a different set of bits. But they both represent the OR of two. The symbol means OR, right? They both represent the ORing of two things together, right? So if I want to say B and C, I say this. And if I want to say A and C, I say this. And they're different. The same number of bits, but they're organized differently because because they're in different parts of the truth table. And you've got other things that are scaling this operation. So like B is the B variable, and the B and D and E are causing this to be much larger than the normal truth table for this, which would be like if you only really cared about this operation, you would have you might however you wanted to represent this. It's actually the same either way. One of these would be your left input, and then one would be the right input, and then you would say your truth table would only be 4 inputs long. This is every combination of 0 and 1 for those two inputs. But because we have these other variables, we have to have a 32-bit truth table. And in fact, if we say A and B, you'll notice that you get this thing repeated. Well, I guess this is many times, 8 times, right? So 8, or just shape of this is 32, and the shape of this is 4. So 32 divided by 4 is 8. And so you see this is repeated multiple times, and that's kind of what I'm trying to get to with an F-Nid, right? An F-Nid has one of these truth tables, but it's like, what do you name your input variables? Well, if you name them A and C, you get this truth table. But if you name them A and B, you get this truth table. And they're the same. It's the same concept, but the truth table is different. Well, this makes sense. This representation makes sense. The 32-bit long truth table makes sense when you're dealing with them as truth tables, as nodes, right? Because say you want to XOR, say you want to take this, right? And then you want to take, say, C and D, right? And then you want to XOR these two things together. Well, you write this, and then you write this, right? And whatever those, so now you got two nodes, right? And then, or we can just say like that. Oh, wrong way. You put them side by side. Well, you want to XOR these things together. You get this truth table. And so you can just do that operation directly on the truth table. Right? And so any two functions, any two 32-bit truth tables can be XORed, can be ANDed, you can do all those operations directly, and you save yourself the work of constructing this weird graph. All right. So that's the concept of, that's the reason for having these. Well, one reason is, as I said, to keep the number of actual nodes you have to create smaller. It's still going to be huge when you have complex functions. You're still going to have lots and lots of nodes, but you can at least, there are this many 2 to the 32 possible, which is about 4.2 billion. Yeah, that's million. Or, sorry, this is, this part is million, and then that's billion. So 4.2 billion possible functions that could have been at the bottom of your BDD now don't have to be, and so you can encode them differently. Okay. Well, that's the goal of that. Okay, I'm rambling again. That was a T node, or that was like the draft one of a T node. All right, so then you've got the truth table in 32 bits, and then what do you do with the other bits? Well, some of the bits are a header, right? So you like say right now, I think maybe 4 bits are being used as a header. Let me see. I've got an invert bit, I've got a variable bit, I've got the T bit, which is really only used to mean a constant right now. If it's a variable, then I say, is it an X variable or a V variable? Is it a real variable or a virtual variable? And then I added this F bit, which was my first crack at whether or not it's a function. The F bit is still going to stick around. Okay, so that's what, 5 bits so far? 1, 2, 3, 4, 5 in the header, right? That's it. Those 5 bits are my header that are on the leftmost side of the, or the high bit. The 5 high bits are used as a header. I'm reserving. I have a bunch of ideas for things I could do with this thing. So, maybe 10 bits should be kept aside. I don't know, but that leaves a bunch of bits that are not kept aside. So right now, I have an area. Right now, it's just everything up to that bit. Ooh. This might be wrong. This might be wrong. But some section of the bits are used as a right. See, this mask is used to figure out what parts are the truth table. The truth table, when it's not being used as a truth table, those parts are called the index, and they're saying like, if this is node number 709, 795432, go look it up in a big array in the database, and it's in that slot, right? That's the slot where it is. And then the idea is you override that to use the truth table for these when the T bit is set. And then on the left-hand side, or the high bits, you have these 5 bits so far, maybe up to 8 bits, maybe 10 bits. I don't know, but that's 10 out of 32 bits being used, right? And that leaves like 22 bits or 24 bits if it, that leaves the rest of the bits free. And so when it's a V bit, I use that, or even when it's just like a BDD bit, like it's a node. It's representing a node in a BDD as opposed to an AST. All right, so remember, this was the AST, and here is the BDD, or down here. And when it's one of these, I actually use it to store what is the variable on which it branches. So if there's 24 bits free to do that, I'm going to cut my head off. If there are 24 bits free to do that, then you can have 2 to the 24. Whoops, sorry. You can have 2 to the 24 possible variables, which is 16,777,216. And that's like 16 million variables is probably enough. If you need a billion variables, well, hack the source code, right? You're gonna have to fork Bex. But I think like so I want to keep that many variables there, right? Like I want to be able to refer to that many number of variables. And I guess if I needed to do more, I would just not store the that branching variable in the NID itself. But you can keep track of that many possible distinctions in there, and that also gives you some. Well, I don't actually do this yet, but the idea would be that like you could replace this with X9 or whatever, and you don't actually have to store a new thing in the database. You just store these pairs. The database only contains the pairs, and the NID fills in the branching variable. So what you have is like it's really an index into a set of high and low pairs. And then if you change this to X3, it would be the same high-low pair, the same index, but a different variable. And that would all be stored in the NID. And so that, again, gives you potentially this many nodes. You can reduce the size of the database, I guess, by this many nodes, by this amount, right? The scaling factor, right? If that makes any sense at all. Because you basically have this, you have 16 million possibilities for the variable to fill in at the top, and that's 16 million different things that you don't have to make a redundant copy of. You shouldn't have to copy it just because it's, well, you wouldn't be copying the whole tree, but you don't have to actually store an extra node just for changing the variable. Okay. So I think I've explained what I'm doing. Okay. So then T-Nids Mark II is the idea that you could take this same concept and any five, and you could make it a function of any 5 input bits, because you have this 24-bit slot to hold. Let me pull up the doc that I wrote. So where's Emacs? I don't have Emacs. Okay. I want to pull up that doc real quick. No Emacs. It didn't launch. This happens sometimes to me. I don't know why. Emacs. And it's going to launch like 3 of them at once. Like it's waiting to launch Emacs. Maybe I hit the wrong button. Come on. Yeah, see, I've got 3 copies of this, but they're not showing up. They finally showed up on my screen. Here. Go. Why that didn't happen? I think I set F10 options. Is it F? Set default font D, capital D. I set that to 16, and we'll get that. And then I load dver specs and docs, maybe. I think I called it FT. I just checked that in on my other computer, and I have not loaded it yet. Let me try this. Maggot is a maggot. I gotta be called maggot, right? Oh, is it called maggot? Oh, that's gross. I thought it was more like magic. Magic. No, it's obviously maggot, right? Oh, that's so gross. Why would you call anything maggot? Anyway, so I should be able to fetch. I should be able to pull, right? Go into main from origin main. Could not read from remote repository. Why not? Because I don't have my, I'm not logged in. So I have to do this. There we go. Third try is the charm. Okay, so can I retry? No. So Magit. I'm gonna say. I say capital F, right? Go from origin main. Alright, so now I have F-Nids. So if I see that, F-Nids notes. Okay, so now that I've explained what all this was, actually let's put it on this side. And okay. So the goals for TNF nodes, TNF-Nids. One is to be able to implement this thing called apply for both AST and BDD nodes. That means apply this thing, apply this function to some inputs. Treat this truth table as if it were a function. And I've started implementing that, and so now I store, for example, the operation AND is actually here in, oh, it's in ops.rs. And so is actually this truth table. It's actually stored as a truth table. And it's a fun nid, so it's got the F bit set. That's an F nid. And with arity 2, and it has this truth table. And then OR has this truth table. Bell is the same as OR. XOR is this truth table. NOR implies, and so on. And I also got a thing over here called simp that looks at I just hand coded some simplification rules for AND, OR, and XOR. And my intent is to generate these for any function. Any of those 4.2 billion functions, you should be able to create a simplification rule like that. It may not make any sense, but it can always simplify from a, if you know that one of the inputs is, if any of the inputs are constants, you can simplify by reducing the arity and just canceling those out. And then if any of them are equal to each other, any of the inputs are equal to each other or equal to the inverse of another, like so if you happen to pass the function like x and not x, right, as two of the inputs, it should be able to see those two things and say, okay, well, I can unify this. I can use the same signal. I can feed the same signal, and I can rewrite the function in such a way that it takes advantage of the fact that these two inputs are the same. And so basically, if the inputs were called A and B, and you pass them both X, then you can just replace them both with A, right? And then now you only have input A. And if you pass in X and not X, then you can replace A with or A with, you just leave A alone, and then B you replace with not A, right? And then you rewrite the function that way. So that's a simplification rule. And then the same thing can happen on a truth table at the truth table level. You just, where's my J interpreter? Did I lose J? No. I lost J somewhere. I must have closed J. That was dumb. Because now I have to. I forgot what the. It doesn't remember what those were. So we just replace them, and then blah blah blah. So we have this input, but if A and B are the same, then we can just replace this with A, right? And then you get something different. Or if A and B are inverses of each other, you can replace one of them with not A. Yeah. I don't think it matters which one is which, right? You just simplifying the function. Okay, so these simplification rules basically are the case where it's a constant, or two of them equal each other, or they equal inverts of each other, and those are the simplification rules. And you also can now do, but because you have 5 inputs, you can do that on any pair of inputs. Can be simplified. So I think there's a good chance that these rules. How do I say this? In Bex, when I'm swaying back and forth. That's the face capturing thing. OBS is doing that on my behalf. What am I trying to say? Well, I think one of the things that makes Bex slightly slower than some of the other BDD packages is that they have an operation called apply, which is this first goal here for BDD nodes, and basically it means you can take any of the 16 binary, or at least these important binary operations, or dyadic operations, two argument operations, and replace them and perform the operation on the BDD very quickly. Whereas what I do is I use the simplification rule once when I'm constructing the AST, or when I'm simplifying the AST. There can be any number of simplification steps where it applies these rules, but when I actually come to do the BDD, they get translated into basically it does it once at the top level. It says, well, if one of these is a constant, then I'm going to treat it that way. But then the recursive step for merging the whole structure of the BDDs is it translates them into an if then else operation. And so then if then else is the primitive recursive function in BDD land, I guess. And whereas the other BDD packages have that, but they also, that's a 3-argument function. You have 3 separate functions that you're juggling, 3 separate BDDs that you're juggling, and you swap them around constantly. And for normalization reasons. Whereas with XOR and 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 OR, you only have 2 operations, and you can simplify along the way. And so I think doing this apply operation will make Bex much faster. I think that's one of the reasons. It's probably the main reason that everybody else is currently faster than Bex, because Bex is having to do more work, even though Bex is multi-threaded and they're not. There's there are a couple of packages that are multi-threaded, but like the big names that were in those benchmarks are not multi-threaded. And yeah, I see it's 9:42 now. I've spent the entire time just rambling about it. I want to go through here, and I'll just keep. I guess I'm not doing any code today. I guess I'm just reviewing what Bex is for the stream. All right, so the other goals for these are, again, function and table nodes. F-Nids are function, T is table. So save space by storing BDDs directly in the NID. I've talked about that. Automatically generate simplification rules. I've talked about that. Apply functions on truth tables themselves using bitwise operators. I think I've talked about that. So you have those 32-bit tables, and you can just AND them together immediately. You don't have to do any of that simplification stuff, because the operation is just I think I say this somewhere in here, but that table, right? Yeah. So X and Y. So if I have a nid called X and a nid called Y, and I want to AND them together, all I have to do is look at their tables and AND those together and create a new nid around that. So that's kind of the idea. So that's applying things directly. And then store functions for AST apply in a compact format. That's the thing I haven't talked about yet. Oh, and I haven't talked about the second part of the truth table. So let me jump here. So the T-bit indicates a table and a set of input bits. So rather than just storing a truth table and always saying these are, A, B, C, D, and E, those 5 particular ones, I want to use the 24 bits I have in the other field, right, to indicate that okay, so this other field is the vid, the mask, or the arity, right? So the vid is the variable index, or the variable ID, right? And however big that field is, I want to include a bit mask. And the bit mask tells me which bits am I talking about. There are only going to be up to 5 of them, but I have my choice about which 5 I look at. So I can't store every possible, because I have to use 1 bit per variable. So I have a field now that looks like this, right? So let's do 20. Let's say that the maximum is 20. So we have 20 possible bits, right? So I have a field that looks like that, and of course we'll encode that as, a number, right? And then decimal places or hexadecimal, right? Okay. So that gets encoded as number 0. Well, what am I trying to say? Basically, if I want to say, well, it's a function of those last 2 bits, I would change this to 1 and this to 1, right? If it's a constant, I say it's not dependent on any bits. If it's dependent on 1 variable, I call it this. And I actually don't use a truth table for this because it doesn't make any sense. Because I already have a thing called a variable that does this. But once your arity, your number of inputs is at least 2, then you can pick which 2 they are. So if they're these 2, then that's this represents x0, this represents x1. I know this is very small because I set this. Now you can't see it for other reasons. All right, so this is x0, this is x1, and basically it's just a set. It's a bit mask. So you look at the number of 1s that are in this chunk of bits, and that tells you how many input bits there are. And then, as long as it's a function, as long as you're applying this to input variables that are numbered x20 or less, or x, in this case 20. I don't know what the exact max is, but whatever that max number is, that's the number of bits in the field. And then you can just pick any 5 of those bits and set them, and that will allow you to store. It will allow you to store in that field a set of 5 bits, or up to 5 bits. So yeah, that's that. Oh, right. So that allows you to use the same truth table, right? So what you'll notice is if they're contiguous, if we say A and B, let's do it like this. A and B, C and D. maybe B and C. C. Well, C and D. Oops. Now, once you do the first one like that, you can just use this. And then we'll do D and E, right? So these I'm about to show you 4 separate truth tables. I mean, you can see them right here, but let's view map them so you can really. And you can see they're basically the same, right? They're basically the same. How do I show you that they're the same? This one is a pattern of, this long is a chunk, and then a chunk and a chunk. So 3 black chunks and 1 white chunk. And here you have 3 black chunks and 1 white chunk, 3 black chunks and one white chunk. Here you have 3 black chunks and 1 white chunk, 3 black chunks and 1 white chunk. They're just scaled, right? And so by shifting the pairs, I'm shifting the window that I'm looking at by looking at different bits. I can scale this bitmap, right? So this is the simplest case at the top, where it's literally 0, 0, 0, 1, 0, 0, 0, 1, and here it's instead of 3 zeros, it's 6 zeros and then 2 ones, and here it's 12 zeros and 4 ones, right, to get it to 16. And here it's 24 zeros and 8 ones, and it's just scaling. It's just doubling the size of these blocks at every step, and that's why it looks very similar to that original pattern that you saw. When I just did A, B, C, D, E, right? Like, it's very similar to this because it's really just looking at the rightmost. It's literally. What I'm trying to say, like, it's a function of this. It's a masking of this. It started with this, and it masked out the ones that were only these two lines were the same, and then it masked out the ones where only these 2 lines were the same, and then only these 2 lines, and then only these 2 lines. So it's a the restriction of this. This turned into this. Right. So what am I trying to say? That, oh, right. Now, I don't have F and G and H and I, J, K, and all these other variables, but if I did, it would just be taking the same pattern and scaling it up even further, right? So it wouldn't change the pattern. It's just scaling it, if that makes any sense. So the actual data that you care about still fits in 32 bits, as long as it's a function of 5 input variables. But how you scale it depends on which bits you assign as the inputs, right? So it's really an abstract function. And you can think of it in the simplest case as it's the function that takes specifically x0, x1, x2, x3, x4 in that order. And that's the general case, all right? And so then you say, now what do I want to plug into there? And there's 2 possibilities. If what you want to plug in, everything you want to plug in is a variable, and the index of that variable, the number of that variable is small enough that it can fit in this 20-bit bit mask, then you can just pick 5 bits and stick them in there, and then that's your truth table. So the general, or the most general case where let's do this. Most general case where you have 5 inputs would be 1, 2, 3, 4, 5. and that's saying I want those specific inputs: x0, x1, x2, x3, and x4. Right, and so this is what I'm calling the T-Nid concept Mark II, where now I can store not 2 to the 32 possible inputs, but I can take so 20 choose 5, is that the right number? No, 5 choose, it's the other way around. 20 choose 5 is written like this times this. I can store that many possible functions without actually creating a node, right? I can just create the link, and it just knows that this is what the node should look like. This is what the graph should look like. That's a lot of potential savings in your graph, right? Basically, if it's any one of these, now you might not necessarily have these nodes, right? And not every node is going to be like that. You're still going to have a bunch of nodes, but and as big as that number is, that's a small slice of the potential number of nodes you could have. But you get it for free, right? You get this reduction for free, and at least early on, you're going to see some kind of improvement. So I hope to reduce the size of my graph structures without having to give up anything. And in fact, I expect it to speed things up as well, because now I'm not grabbing a bunch of different things from memory. I'm not looking at a hash table. I'm just directly dealing with bitmaps. So that's the T-Nids. I think that's everything I ever wanted to say about T-Nids. F-Nids now add one more concept, and that is if the inputs are not just raw variables, or they are raw variables but they're not in this range, then I need to store them external to the NID. I need to say, okay, I need to construct an AST node that says I want to apply this thing as a function to these inputs. And I've already been doing that. That's how the AST is stored to begin with. And right now it says, like, you saw it creates, here's the input 1, here's the input 2, and then here's the function that goes in the box or in the circle, to create something like this, right? So we said x0, go x0, and now, or here, x2 and x1, and you XOR it. Well, that creates a node. Right now, that creates a node that says, okay, here's the function I'm calling. Here are the 2 inputs. And in practice, that's stored as a list of those 3 things. So it stores x1, x2, and then it stores an F-Nid, right? It stores a special op that says this one is not just a NID. This is a NID that I'm using as a function, and it is the NID for not equals to, or XOR. And so specifically, it's got the F-bit set, and then the truth table is set to the XOR truth table. Which is, again, in ops, and it's called XOR, right? So it's this truth table repeated many times. So you say A XOR B, it's that truth table. Now, if you want to view map that, right, it looks like this. It looks like a stripe. Looks like a set of stripes. Actually, the white stripes, the ones are slightly offset, right? So it goes 0, 1, 1, 0, 1, 1. So yeah, that's the truth table. And it's just repeating. It's just repeating. So I think of, technically, the truth table for A XOR B is 4 items long, right? It is literally, it should be 0, 0, 1, 1 XOR 0, 1, 0, 1. And so it's that. That's the truth table. And so this thing that is like this extended truth table, I think of this not just as a truth table, but also as a repeating pattern, a signal that propagates over time. Just like you might say, like a sine wave, for example, right? Like it actually can be, it's a cyclical thing. It's not just a truth table, it's a signal passing through time. And that's how I conceptualize this thing. And so this actually goes on forever, and we're looking at a slice of it. And had we been talking about more than just 5 variables here, had I defined you know, when I defined A, B, and C and D and all that stuff, I used the expression that looks like this. I said something about 2 to the 5th power. Well, if I said 2 to the 15th power, it would be 65,536, or sorry, 16th power. It would be 65,536 values long, bits long, which is about 4K, I think. I don't know. No, it can't be 4K. Whatever. 2 to the 20th would be about 8K of memory. So what am I trying to say? Signals, right? So signals are this propagating thing over time, and I use them as signals because rather than truth tables, because I want to be able to apply those bitwise operations to the entire 32-bit table, right? And so by using a signal, you know, the replicated truth table, rather than just the truncated truth table, which would only be 4 bits long, now I can apply that to I can combine any number of bits that way. If the masks, if these masks of saying what the inputs are match, then you can just do the operation directly. If you have different sets of inputs, then you're operating at different scales, and so you have to actually scale the output, and you might wind up with a function. The result might be a function that, well, like for example, if you have this thing, right, and then you combine it with something over here that is using, what am I doing? That is using, you know, this thing. Well, these overlap, but you've got 3 overlapping ones, and then you've got 4 non-overlapping ones. So you actually have a function now of 7 variables, and so you can't stick that in this size truth table anymore. You need your truth table to be 4 times as big, because you're adding 2 extra bits, so you have to double it twice. And so now you need 128 bits to store that truth table. And that no longer fits in the NID. Therefore, there needs to be some bigger concept. If we want to keep going with truth tables, there needs to be some bigger concept that stores an arbitrarily long truth table. I do have that idea. That's called I'm calling that a reg base. It does not exist, but I have the idea, and I plan to make that. So reg base, the way here at the bottom. And I haven't completely fleshed that out, but that's the idea. That probably up to about 24 bits, 20 bits, 24 bits, something in those lines, you know, where the things start being like, you know, after about 8 kilobytes, it's like, well, I mean, you could have a truth table that, you know, takes gigabytes, and that's no problem. But the problem is that you need one of these things for each node that you're dealing with, and so, you know, you might need thousands of these things, and so keeping them, you know, keeping a limit on them is probably for the best. Anyway, so that's the idea of an expanded truth table. That is not part of this. That's not fitting in a single NID. An F-NID is when you say, I'm going to apply it to something, but I don't yet know which inputs I'm going to apply it to. Therefore, I'm going to, well, okay, so that's an FT-NID, what I'm saying. So I'm going to take that truth table. It's an F-NID, it's a function, and it's a truth table. And I'm going to apply that truth table to an arbitrary set of inputs. So when I store the truth table, I'm just going to treat it as if I were dealing with those, you know, I'm going to rewrite something like this. And if I wanted to convert this into an F-NID, I would use this form, right? I would move the variables down and scale the truth table so that the input mask is like this, and then I have 5 input variables, and they're specifically the signals x1, x2, x3, x4, and x0. That's that. Then, okay, so that's the concept of an F indicates a function to be applied to arbitrary inputs. They're not mutually exclusive. What I've been talking about so far is F and T together. I've been talking about T and F and T together. F without the T, it just means that one of the nodes that I'm using that I've already stored in my AST or my BDD or something like that, some node out there somewhere in one of those bases represents a function, and it's way too big to fit in a single node, but I'm going to use that as the function I'm talking about. And so that's like making a subroutine call in a way. It's like making a component, right? We're saying, okay, I want to define this big complicated function, and I'm going to use whatever I want to do. Like if it's an addition, if you're doing 32-bit addition, you have to do a lot of like graph stuff to build like all the carry bits and the result bits and all that. But you're doing 32-bit addition, you're going to have 32 separate functions that each produce 1 bit, right? And they might be interrelated, but each of those can now be one function, right? And so then any optimization, so if you do a bunch of additions of 32-bit registers, right, then maybe you can find some way to optimize those functions, and you get the benefit of optimizing them everywhere you do the addition, rather than having one gigantic sprawling thing that has these where every single time you do an addition, you have to redefine it in terms of and or and XOR and all those things. So now you can have these higher order functions, or not higher order, higher arity functions, where you have like multiple inputs and they're more complicated functions. And so you can refer to them, you can give them a name or an ID, whatever. So that's what I don't yet have a plan to implement. Do I have a plan to implement that? Well, I do, because I want to be able to say, well, like, okay, I want to give a name to this particular thing, right? Again, the like a carry bit, like a 2-bit adder, like or what am I trying to say? An add with carry that has 3 inputs, and it produces a result bit and a carry bit. So I need to know the result bit and I need to know the carry bit, right? And those are 2 separate functions, and I can refer to those functions over and over again. And well, actually, that in that particular case, it's simple enough that for just the 2-bit adder, that's simple enough or it's called a full adder. Sorry, a full adder takes 3 input bits. It takes a carry bit and it takes the 2 input bits. So that's simple enough that would fit in a single NID, because it only has 3 inputs. It has 2 outputs, so you would have 2 NIDs, one for the carry, one for the result. But then when you chain them together, and you're doing like a 4-bit adder or a 6-bit adder or whatever, a 32-bit adder, well, those 32 output bits, you actually don't care about the carry bit at that point. You just want the results. So those 32 result bits would, and same thing for multiplication, would have their own sets of inputs, and you would apply them to different variables, and you could optimize them independently of each other. Like, for example, if you know that, so again, in the case of like factoring a number, same thing for multiplication, right? So you would have a multiplication table, right? And so you do a 32-bit multiplication, you get whatever, you get your 64-bit results. So you have 64 functions that represent inputs, right? So I'm sorry, they represent the output of the multiplication, 64 output bits, and you would, I'm overloading my brain here trying to put this into words. Like, maybe you can find out, maybe you just happen to know that, like, one of your constraints is that input bit number 37 is going to be a 0, right? All right, so you can, so for all these individual functions where you know it's going to be a 0, or you've chosen it to be a 0, you're searching that space where it's a 0, you can fill in the 0, right? And then you can optimize, quote unquote, optimize that function by simplifying it, by performing one of these simplification rules. So here you've got, the rightmost bit has two inputs. The second bit, the lowest bit has two. The lowest output bit had two inputs when you do multiplication, right? Like, an even times an even is an even times an odd is an even, and an odd times an odd is a one. So you had you only had to look at those last two bits of the inputs to find out what the bit of the output is, right? But then the next bit you have to worry about those first two input bits and the second two input bits, the second column of input bits, and so on. So bit n depends on, as you go from right to left, from low to high, depends on 2 times n inputs. And so when you get to number 32, the leftmost I can't be right. Oh, it is right. So up to the leftmost, up to the number of input bits. So you multiply two 32-bit numbers together. So the first 32 are going to depend on, the first one depends on 2, the next one depends on 4, the next one depends on 6, and so on, because everything moves right to left. And then you get to number 32, and you're depending on all 64 input bits. And then as you keep going, you've got carry bits to deal with, and so they also deal with everything to the right. And so you've got 32 bits, 32 separate functions that only deal with the results of the carries, right? But those results depend on all 64 input bits. So there are 33 functions that depend on 64 bits, one that depends on 62 bits, one that depends on 60 bits, and so on and so on and so forth. Yeah. So those are big functions. The truth tables are gigantic because they're 2 to the 64 bits wide, or 2 to the 64 bits wide on those last things. So they're gigantic, right? So anything you can do to constrain them by solving the right-hand side first. So example, if you're, again, with my primordial thing, Bex does not do this. This is a thing that could happen, that could be done. You could say, well, okay, the rightmost output bits, the low bits, are constrained by this. I can see that they only depend on 2 bits, and well, only this particular pattern of input bits would give me that last bit, right? Again, even times even, or even, like if it's an even output, which it is because it's a primordial, and primordials contain the number 2, then one of the 2 inputs had to have a 2 in it, right? You don't know that both, it could be the case that both of them do. It doesn't know that. It doesn't know that there's only 1 2. It just sees that it's an even number, therefore at least one of the inputs was even. So they can't both be odd, and they can't. Yeah, but they could both be even. So you of 4 cases, you've eliminated one of the 4 possible cases for the 2 input bits. If it were odd, it would actually be easier to factor for that reason. Slightly easier, right? All right. So anyway, so then the thought would be, well, now you could take that constraint and you could apply it as you go to all of the functions and simplify all of them. I don't know. Yeah. So that's that doesn't sound like much, but basically anytime you can eliminate a bit, you're cutting a truth table in half. And in this particular case, we're eliminating like half a bit. So it doesn't cut the truth table in half, but it does reduce the amount of work, a search space that you would have to explore for every bit to the right or to the left of that. So all the higher bits. I guess I'm kind of rambling. I'm kind of brainstorming. Like this has gone through my head before, but this is actually a little off. I haven't gotten to that point yet, is what I'm saying. So anyway, so I think I've explained what T and F are. So T is truth table, F is a function, and it's taking either a truth table or just an arbitrary node and applying it to inputs that you don't know yet. You don't know what the inputs are yet. And one thing you can do, though, is you can normalize the set of inputs, even the function itself. So if the function is, you're taking an expression and you're converting it into a function. And what you can do is you can rename all of the free variables, the unbound variables in that function, and renumber them so that they're what I call solid, right? Which is like this, where it's, you've got a row of ones. If you were to write that bit mask, it would be a solid range with no gaps, starting from x0. So this bit mask represents x0, x1. This is x0, x1, x2, x0, x1, x2, x3, and then x0, x1, x2, x3, x4, right? And then likewise that, that concept applies for like this specifically is referring to the inputs for truth tables, because you can only have five input bits. But the same concept applies, like even if you had just like a gigantic expression of, well, again, like, adding, right? So if you have an adder, right, you might name your input variables x0 through x31 and y0 through y31. But then you might take the adder and add something else to it. So you might add three numbers together. Well, you're going to reuse that function, and now you've got different inputs. And so rather than store a completely new graph, you take the abstract graph and you just slightly normalize it a little bit so that you just write the expression as if it were only in terms of, I said x0 and y0. Well, really it's just x0 through x63, right? And it doesn't matter what order you put those bits in. It's just some expression of x0 through x. I mean, you have to always use the same ordering, but you have to have a convention. But once you have the convention, you just always use that same convention. And then you arrive at the solution, right? You write the generic expression so that you can put. It's as if you're putting, I don't know. Is this called lambda? So you have like a plus b. Well, you want to change it to lambda. Well, I guess lambda a, right, would be lam. Or toggle pretty. First of all, lambda is not spelled that way. Yeah, so lambda a, lambda b, I think it's like this, right? And calculus, right? And then a plus b. So you can take the expression that is just an expression of free variables and you turn it into a function by doing this. Well, the thought then is that rather than saying C and B, you just always say A and B, and it doesn't matter which way it's assigned as long as it's consistent. You have two separate functions. This and this would have two different truth. We can make this XOR, right? Well, these actually would have the same function, so we'll have the same truth table because, right? These have the same truth table, but these have different truth tables, right? Because like the order that they're in matters, right? I think I'm saying that right. So my thought was to as a normalization step, you would always do it this way, right? So you would always put x1 you know, so f of x1 is really f of, you know, we're going to set that to f of x0, and then we're going to say x0 plus x1. So that, I don't wow, okay. It's x1 greater than x0, right? In this particular, if I'm translating, I'm keeping this correct, right? I'm keeping this the same function, right? Something like that, something along those lines. No, it's not right. X0 is less than x1, meaning that x0 is 0 and x1 is 1. That's the only way that you can be less than, right? It means not a, B and not A, basically. Okay, I've been rambling for quite a bit about all this stuff. I did not do any code. I meant to actually jump in and write some code tonight, but I haven't talked about Bex in a while, and I don't have any recordings about what Bex even is, so I guess I was doing a review of what Bex is and what these T and F-Nids are. I think I've covered that. If you want to read this document, it's up on GitHub. It's just in the docs folder. So github.com Bex under doc, or sorry, TangentStorm Bex under doc, and it's called F-Nid notes. It's a little ugly. It doesn't really format that well. These are some test cases about what goes in the different slots, and raw is probably better. If you have Emacs org mode, it'd probably look a whole lot nicer. But anyway, there you go. Yeah. Most of the rest of this just talks about like what like it's kind of documentation now, and then some design choices. Like I had to think through like, you know, how to actually store these things, and, you know, do I want the tree? One thing I'm still worried about is like this, you know, for all this I have it pretty much, I know what I want, but like if I'm saying x1, this is x1 and x2, or sorry, or x2, vel x2. So this I know what it is when it's x0 and x1, but what do I do when it's what actual truth table do I store? And I think it's this. I had written it like this, and I think it should be this, because I want to treat it as a signal, right, rather than just a table. So I need to work that out. And then in Bex itself, the prior commit, as of this filming, is right now Bex commits on May 3rd, 2023. That's today as I'm filming. And then so last week or a week ago, I did this. I introduced the idea of these F-Nids that are called fun and nid fun, and I made some types, and I got it to compile and cleanly, and it's actually quite a bit of code. And I implemented apply for ASTs. I don't think it works. I have some code outside of like some test code that I have not turned into a test case. I was exercising this, and I was able to run the program, but I didn't like write a good clean test case yet. Anyway, so I've made a start on this, and I have actually implemented things like what happens if you some of those simplification rules, like what if you swap the inputs to a function, or you pass in a you know, given a function, return the function you get if you inverted one or more of the input bits. So if you know you're passing in like not something, just remove that not, right? Just simplify it a little bit. Things like that. These are functions specifically for 32-bit truth tables. And I wrote some J code to make it happen. You can see there's that same thing to generate the bits right there. And then now it's like do some stuff with the indices. Like, so this is like this is the you know, x equals not y or something case, when you can see that they're opposites of each other? How can you simplify the function? And I think what I'm going to do eventually is make a little a better pattern matcher here. But I want to get this under test, and then once I do that, I'll replace these tables. I'll consider replacing these tables with a generic function that does the rewrites using a loop. Anyway, so a lot of code here that is a start on implementing this idea. I just wrote the code, and I realized later that I was kind of unclear on the distinction between like truth table versus function versus truth table that is also a function. So that there's actually 2 bits, and so I'm pretty clear on it now. And so this needs to be revised and tested, and that's probably what I'll be doing soon. I had, prior to this, when I was back on Twitch, I had been working on a different series of videos. I had to do with SAT solving in J. I'm still working on those, but I suspect I will not be doing them on stream, at least for a while. I'm interested in doing them. I don't know if I want to stream them because I want to make videos that are scripted with JPress, and so yeah, I kind of want to do that off camera and then present the finished work. I don't know. I'm still debating that, but for now I'm going to do this. When I get bored, maybe I'll switch to something else. Or when I finish, I'll switch to something else. I don't know. And anyway, thank you for watching. This is my first YouTube stream in quite a while. Or I guess I did a test one today just to test the software. I will be doing this every night, and I'm sorry, 4 nights a week for the foreseeable future. I stream Monday, Tuesday, Wednesday, Thursday, and then sometimes I do pop-up streams. But like every night, those 4 weeknights at 8:30 is my usual time, and then whenever else, if I happen to have time, like on the weekend, I might do an extra stream or something like that. I don't normally run this long. I guess I had a lot to talk about. So there you go. This was like a 2-hour video now. So I see now that I can schedule my next video. So I guess I will write up what I think I'm going to talk about, and make that the topic for the next live stream. And then you'll be able to see when it is, and even have YouTube notify you that you can, that it's coming up if you care to watch it. I don't expect anyone is watching this right now, but people have told me they like listening to these things unedited rather than me recording them and then uploading it without all the pauses, and then my head jumps around like Max Headroom. I don't know. Some people seem to like this, so thank you if you do. It certainly helps me to sit here and talk through the ideas in my head. Like, I spent most of the day writing this document, and I started a little bit of it over the week I was on vacation. But writing it and now talking through it has really helped me clarify my ideas. So having someone potentially listen to this is like reason enough for me to do that. It kind of like gives me an excuse to talk through everything. So I appreciate it. Yeah, thanks for watching, and subscribe if you want, and get notified when I do this again, which will be quite often. So that's it. Good. See you again soon. What does that say?